In this chapter, we're going to look at Newton's laws of motion. Newton's laws of motion. These are laws that relate forces and motion. These are laws that relate force and motion. So far we've been dealing with motion in the previous chapters. So let's define force. Force, in layman terms, you can say it's a pull, a push, a squeeze, and so on. So in layman terms, you can say it's a push, a pull, a squeeze, and so on. Okay, but in scientific terms, force is something that causes change of motion or change of shape. So in scientific terms, force is something that causes change of motion or change of shape. Something that causes change of motion or change of shape. Okay, so when you throw an object, you're changing its motion. When you squeeze an object, you're changing its shape. But in this chapter, we're going to concentrate on the change of motion aspect of force. So let's state the unit of force. The SI unit of force is the Newton, after Isaac Newton. Is the Newton, and it's abbreviated by capital N. Okay, so the unit of force is the Newton. It's abbreviated by capital N. All right. Now let's look at the laws of motion from Isaac Newton. So let's state this laws of motion. The first one is called Newton's first law. The second one is called Newton's first law. This law states what happens when there is no force acting on an object. That is, when the net force acting on an object is zero. When there is no force acting on an object, two things can happen. Either it remains at rest, or if it's already moving, it moves with a constant speed in a straight line. So an object will remain at rest or move in a straight line with a constant speed unless acted upon by a net force. So this law says that an object will remain at rest, or move in a straight line with a constant speed unless acted upon by a net force. So this law states what happens when there is no force acting on an object. If there is no force acting on an object, the object either will remain at rest or move in a straight line with a constant speed. So that tells you the effect of force is either to change the speed or to change the direction of the object. And then the second one is Newton's second law. And this law states that what happens when there is a net force acting on an object. Of course, the effect of the force is to change the motion or to produce acceleration. And this law states that the net force acting on an object and the acceleration produced by the force are directly proportional. Okay, That is, when you double the force, the acceleration doubles. When you triple the force, the acceleration triples, and so on. So this law states that the net force acting on an object is directly proportional to the acceleration produced by the force, Okay, so mathematically we're saying the force acting on object is proportional to acceleration. It's a symbol of proportionality. And the mathematical implication of proportionality is that the ratio is a constant, you see? So this means mathematically the ratio between the force and the acceleration is a constant. That is, the force might change, the acceleration might change, but the ratio will always remain a constant. What that means is if you double the force, the acceleration doubles, the ratio remains a constant. If you triple the force, the acceleration triples and the ratio remains constant. Okay, so this constant is a measure of the amount of matter the object has, and it's called mass. This constant is a measure of the amount of matter an object has, and is called the mass of the object. Is called the mass, again, is M, of the object. The mass of the object. Okay, so we can write as the ratio between force and acceleration equals to the mass of the object. But this one is customarily written as F equals ma. Okay, but remember, force is a vector quantity. This is a one-dimensional equation, so we have to write the vector form. And remember, if there are a number of forces acting on the object, this force represents the net force acting on the object. That is, you add up all the forces, that is what equals to mass times acceleration. So in vector form, we can write this equation as, in vector form, this is the net force, the sum of all the forces acting on the object, equals mass times acceleration. So this is the mathematical statement of Newton's second law. The vector force acting on the object is equal to the mass of the object times acceleration. Okay, so let's look at unit of mass now. Unit of mass. Obviously, it is the unit of force, Newton, divided by the unit of acceleration, which is meter per second square, and that is defined to be the kilogram, or abbreviated by kg. Okay, so a 1 kilogram mass is a mass that accelerates with an acceleration of 1 meters per second square when subjected to a force of 1 Newton. Right? Now this is vector form. If you want, we can write each in the IJ notation and use the vector equation, but also we can decompose this equation into two components, the horizontal component and the vertical component, or the x component, the y component. Okay, so let's write this equation in component form. In component form, we have F net equals ma. Now, if there are a number of forces acting on the object, what this means is you add up all the forces, okay? You add up all the forces, and that equals mass times acceleration. Now, if two vectors are equal, obviously their x components are equal and the y components are equal. So we can write this in component form as follows. In component form, So these two vectors are equal, their x components are equal. So we can say the sum of the x components, 2x plus f3x and so on, equals mass times the x component of the acceleration. The same thing with the y component. We have f1y plus f2y plus f3y and so on equals mass times the y component of the acceleration. So if you want, we can express these forces in the Ig notation and use this vector equation. But another way of doing it is you just deal with two scalar equations, an equation for the x component and an equation for the y component. So this is the component form of Newton's second law. Okay, and instead of a single vector equation, we can reduce it to two scalar equations or algebraic equations. Okay, and then let's look at Newton's third law. Newton's third law. I think everybody knows this law. This law says that for every action, there is an equal but opposite reaction. This law states that for every action, there is an equal but opposite reaction. For example, let's say this object A and B are colliding. Okay, let's say this is A and this is B. Let's say this object are colliding. So obviously this object will exert force on this object. Let's call that force exerted on A by B, and also this object will exert force, object A will exert force on object B. Let's call that the force on B by object A. So what this law says is these two forces have the same magnitude but opposite direction. In other words, they're negatives of each other. So these two forces are related as follows. They're negatives of each other, equals the negative of BA. Okay, so this is the statement of Newton's third law. When two objects exert force on each other, such as in a collision, the forces exerted by one object on the other is equal but opposite in direction to the force exerted by the object on the other. In other words, both objects have the same magnitude but opposite direction. All right. Now, these two forces, even though they're opposite, they don't add up to zero because they're acting on different objects. You see, this force is acting on this one, and this force is acting on this one. Actually, both will accelerate because this you have this force acting on this one that accelerates it. You got this force acting on this one that accelerates it. So these forces cannot add up to each other because they're acting on different objects. Okay. So the major problem in solving problems have to do with Newton's second law is in identifying the forces. So let's start by looking at types of forces, okay, so that we can identify the forces easily. So let's look at types of forces. Forces can be classified into two parts. You can classify them into contact forces and non-contact forces. Contact and non-contact forces. Well, contact forces are obviously forces that exert force by touching the object, and non-contact forces are forces that exert force on the object without touching the object. So first let's start with non-contact forces. Non-contact forces. These are usually natural forces. Examples include, an object falls towards Earth even though there is no connection between Earth and the object. So one example is gravitational force. Gravitational force is a non-contact force. It can exert force without touching the object. Another example is electrical force. Electrical force also can exert force without touching an object. If you comb your hair, the comb will develop the property of attracting a piece of paper without touching the piece of paper. Another natural force that can exert force without touching an object is magnetic force. You see, a permanent magnet can exert force on a piece of metal without touching the piece of metal. Okay, so these are some the examples of non-contact forces. Now, in this course, we're going to deal only with the gravitational force. In this course, these two forces are dealt with in the second part of the course. So let's look at gravitational force. On the surface of Earth or the surface of any planet, we call this type of force weight. So let me start by defining weight. Now, there is another law from Isaac Newton, it's called gravitational law from Isaac Newton. That there is another law from Newton that's called gravitational law. It says that any two objects in the universe attract each other with a force that's proportional to the product of the masses and inversely proportional to the square of the distance. So any two objects will exert force. Okay. Now, when we talk about the weight of an object, let's say on the surface of a massive object, even though every object on the surface attract each other, the gravitational force exerted by the massive object is much bigger than the other forces. So we can just say weight is gravitational force exerted by the massive object in the vicinity. For example, for an object on Earth, on the surface of Earth, we can say weight is the gravitational force exerted by Earth. On the moon, we can say weight is the force exerted by the gravitational force of the moon and so on. So let's define weight. Weight is gravitational force, let's say weight of an object, is the gravitational force exerted on the object by the massive object in the vicinity. Massive object in the vicinity. So what this means is the weight of an object on the surface of Earth is the gravitational force exerted by Earth. The weight of an object on the surface of Mars is the gravitational force exerted by Mars, and so on. Okay? So let's represent this weight by W. Okay? Let's represent weight, and it's a vector, is a force. Now, this is a force. So according to Newton's second law, this should be equal to mass times acceleration. Okay? But we know that on the surface of Earth, the value of gravitational acceleration is g, okay, which is 9.8 meters per second square, okay, and this direction is always towards the center of Earth, so you can say maybe in the negative j direction, okay. So with that, we can express weight as follows. Weight equals mass times gravitational acceleration in the negative j direction, okay, because it's always directed towards the center. So this would be the formula for weight on the surface of Earth, okay. It's in the negative j direction because it's directed towards the center of Earth, alright. So that's the formula for weight. The weight of an object on the surface of Earth is mass times the gravitational acceleration on the surface of Earth, and is always directed towards the center. Gravity is always an attractive force. If the object is on the moon, then this will be the gravitational acceleration on the surface of the moon. Now we're going to look at the difference between mass and weight. Difference between mass and weight. Now, mass is a property of the object. It's a measure of the amount of motion the object has. Okay, so it doesn't depend on anything else. It's just the property of the object itself. It's an inherent property of the object. But weight depends on something else. It's force exerted by the massive object in the vicinity. So mass is always the same whether the object is on Earth, on the Moon, or on Mars, because it's a property of the object itself. But weight would be different on different planets because it's force exerted by the massive object in the vicinity. Okay, so that's the difference. So the difference is mass is the same on different planets, is the same on different planets because it's just a measure of the amount of matter the object has, and that doesn't change because it is a measure of the amount of matter the object has. Okay, and that doesn't change. Amount of matter the object has. Okay, and that's always the same. All right. On the other hand, weight is different on different planets because it's force exerted by the massive object in its vicinity. It depends on something else. But weight is different on different planets because its value depends on the massive object in its vicinity, on the massive object in its vicinity, okay? So that's the basic difference between mass and weight. Mass is always the same, but weight is different on different planets because it's force exerted by the massive object in the vicinity. For example, the weight of an object on the Moon would be 1/6 of the weight of an object on the Earth because Moon is smaller. Okay. All right. Now we're going to look at contact forces. Contact forces. These are trivial forces, the forces exerted by objects touching the object, okay? But there is one kind of force that requires special attention, and that is surface force. So we're going to look at surface forces. Surface forces. These are force between objects in contact, sliding on each other. These are forces between surfaces in contact. Surfaces in contact. For example, take this object. Let's say this object is lying on the surface of the ground, like this. Now the surface is doing two things, okay? First of all, it's supporting the weight of this object. You see, gravity is pulling down, okay? But that force is being counterbalanced by the surface pushing up. That's why this object is not being pulled down, okay? So this surface over here is pushing up, okay? So this force, which is exerted by the surface on the object, is called the normal force. It is perpendicular to both surfaces. We call this the normal force. So normal force is perpendicular to the surface, okay? So normal force is basically the force pushing the two surfaces together. This is the force pushing the two surfaces together. Pushing the two surfaces together, okay? and is perpendicular to the surfaces. It is perpendicular to the surfaces. It is perpendicular to the surfaces. Okay, so you see you've got the gravity pulling down, okay, but the surface pushing up. That's called normal force. And then if you try to pull this object to the right, let's see what happens. There is a force going to resist you, okay? That is the resistive force exerted by the surface. That's called the force of friction. So we have another force parallel to the surface that we call friction, okay? So what we call surface force is a combination of these two, okay? So you got a perpendicular force that we call normal force, and you've got a horizontal component that we call friction, okay? So you can say normal force is the vertical component of the surface force, and friction is the horizontal component of the surface force. So you see the surface force is here. You see, you add these two forces together. This is the surface force. This is the surface force. Okay. So it has two components. Its vertical component is called normal force, and its horizontal component is called the force of friction. Right? But these two forces are related. Experiment shows that the greater the pressing force between the surfaces, which is the normal force, the greater the force of friction. If you double the pressing force, then the amount of force required to slide this object doubles. If you triple the pressing force between the two surfaces, then the force required to slide this object also triples. So friction and normal force are directly proportional. So friction and normal force are directly proportional. Okay, so if I use F for friction and N for normal force, the force pressing the two surfaces together, then we're saying the force of friction is proportional to the normal force. That is, if we double the normal force, friction will double. If we triple the normal force, friction will triple, and so on. Mathematically, what this means is the ratio remains a constant. This is a constant. That is, if you double the normal force, this will double, so the ratio remains the same. If you triple this one triples, so the ratio always remains a constant. This constant is a property of the surfaces, and it's called the coefficient of friction of the surfaces. This is coefficient of friction of the surfaces. And we're going to use the Greek letter mu to represent it, okay? So we have the following equation. The ratio between force and normal force equals mu, but this is customary written as friction equals mu times n, okay? So this quantity mu over here is a constant that you can find in tables in textbooks, okay? It's just a function of the surface. For given surfaces it will be constant, but for different pairs of surfaces it will be different. Okay? Now, there are two kinds of coefficient of friction. Two kinds of coefficient of friction. Okay, so let's look at these two kinds of coefficient of friction. Suppose, let's say, you have this object on the surface over here, and you're trying to slide it by applying force over here, but you start the force from zero. Okay, so obviously first it's not going to move. Okay, let's say this force over here is F over here. All right, now first it's not going to move, so you're going to increase it until it moves. So we keep increasing it until it just moves. Okay, But once it starts moving, the force needed to keep it moving decreases. Okay, so it'll be like this. So the force needed to just keep it moving is bigger than the force needed to keep it moving. Okay, so that means we have two kinds of friction: the friction that exists when the object just starts moving, and the friction that exists once the object starts moving. Okay, so we call this force over here static friction. Static friction. Okay, the friction that exists when the object just starts to move, and the friction that exists when the object is moving is called kinetic friction. Kinetic friction. Okay, so let's use Fs for this one, static friction, and Fk for this one, kinetic friction. So you see we have static friction is greater than kinetic friction. Okay, the friction that exists when an object just starts moving, and the friction that exists when an object has already started moving are different, and the static friction, or the friction this is when the objects that start moving is bigger than the kinetic friction. All right. So because of this, we have two kinds of coefficient of friction. One is static coefficient of friction, which is the static friction divided by the normal force. Okay. And then we have the kinetic coefficient of friction, which is the kinetic friction divided by the normal force. This one is called static coefficient of friction, and this one is called kinetic coefficient of friction. Kinetic coefficient of friction. Okay, and since the static friction is bigger than the kinetic friction, we have the following relationship. Okay, mu s equals mu k. So if you're dealing with a problem when an object is just starting to move, you have to use this coefficient of friction. But if you're dealing with a problem where an object is already moving, then you have to use this coefficient of friction over here. Okay. Now let's look at some other properties of friction. Some properties of friction. Some properties of friction. Okay, we have stated some of them already. One is friction is proportional to normal force. Friction is proportional to normal force. That is the force to the force pushing the two surfaces together, to normal force. That is, friction is proportional to n. And friction depends on the nature of the surfaces. You know, sliding on ice is not the same as sliding on a floor. So friction depends on the nature of the surfaces. Depends on the nature of the surfaces in contact. Nature of surfaces. The other property is friction does not depend on contact surface area. Friction does not depend on the contact surface area. Contact surface area. Let's say you're trying to slide a book on the surface. So whether you put the book like this or you put it like this, the friction will be the same. It doesn't depend on the contact surface area. Okay? And then the other property is friction does not depend on the relative speed between surfaces. Friction does not depend on the relative speed between the surfaces. Okay, so what it means is, let's say this object is sliding on the surface over here. Whether this object slides at the speed of 10 meters per second, 20 meters per second, or 100 meters per second, friction is always the same. It doesn't depend on the relative speed between the surfaces. So these are some properties of friction. All right. Now, we're going to use two kinds of motion. The first one is called statics, static object is at rest, and second is called dynamics, static object is the accelerating study of accelerated objects. So we're going to start by looking at statics, then we'll look at dynamics. Statics. Statics, this is the study of objects in equilibrium or at rest, of objects in equilibrium. Equilibrium basically means there is no net force acting on the object. That is, there are two possibles. Either the object could be at rest, or it could be moving in a straight line with a constant speed. Okay, this kind of equilibrium we call translational equilibrium. So let's define it: translational equilibrium, as opposed to rotational equilibrium that we discuss in later chapters. So an object is said to be in translational equilibrium if it's either at rest or moving in a straight line with a constant speed. So this means an object is either at rest or moving in a straight line with a constant speed. Remember Newton's first law? Newton's first law says that this happens when the net force acting on the object is zero. Newton's first law says that an object will remain at rest or move in a straight line with a constant speed unless acted upon by a net force. So the condition for this to happen is that the net force should be equal to zero. Okay, equal to zero. That is, if you add up all the forces acting on the object, okay, then they should add up to zero if the object is in equilibrium. It's either at rest or moving in a straight line with a constant speed. Okay, so we can use this vector equation. Maybe we can express the forces in the Ig notation and use this equation, or we could decompose this equation into two algebraic equations. Okay, so if the sum of the forces is zero, then obviously the sum of the x components and the sum of the y components is also zero. So we can say in component form, we can write this as follows. The first one is the sum of all the x components, and so on, equals 0, and the sum of all the y components equals 0. Okay, so this is the component form of this condition. So if you know that an object is in equilibrium, that is, if you know it is either at rest or moving in a straight line with a constant speed, you can use these equations. So you have two equations, that means you can solve for two variables. Okay, so let's consider some examples to demonstrate the use of these equations. Okay, example. Suppose, let's say you have this object hanging by means of a string. Okay, let's say this is a 10 kilogram object. All right, so this object is obviously at rest. Okay, So the net force acting on it should be 0. Alright? So first let's identify the forces acting on it. Well, obviously gravity is pulling down. That is the force of weight. Okay? And then of course we've got the string pulling up. We call that force tension. Okay, so we have this force which is pushing up the tension in the string. Okay, those are the only two forces. And since we know it's in equilibrium or rest, since it is at rest, it follows that the sum of the forces acting on this object should be 0. So we have the following equation: tension T plus the weight equals 0. Okay, so weight equals negative mg in the j direction, right? So we have the tension minus mass times gravity in the j direction equals 0. So the tension would pull up by this by an amount equal to the weight, but in that direction. Okay, and then of course mass is 10 kilograms and gravity is 9.8, so that will be 10 times 9.8, that is 98 newtons in the j direction. So the direction of this force is in the j direction. So this is using the vector equation. If we rather use the component form, you see these two forces don't have x components, okay, because they're vertical forces. So the component form like this: Ty plus Wy equals 0. This is a component form. Now we know that we don't know the tension, but we know its direction. Its direction is 90 degree. Okay, 90 degree. The weight, we know its magnitude is mass times gravity, and also we know its direction. Its direction is negative 90 degree. 90 degree in a clockwise direction. Okay, it's negative 90 degree. Okay, so Ty would be the unknown tension T times sine of 90, which is the magnitude of the tension T, and Wy is this magnitude mg times the sine of negative 90, okay, which is negative mg. Okay, so with that we get T minus mg equals 0, which gives us T equals mg. So that is the tension, which is 98 newtons. Okay, that's the magnitude of the tension, and the direction of course is upward. All right. Another example. Suppose, let's say, we have this object. Let's say, once again, it's a 10 kilogram object. Now it's being pulled by unknown force to the right, but we know it's moving with a uniform speed. It's moving with a uniform speed. Okay, and also we know the coefficient of friction, let's say, is 0.2. Okay, so the question is calculate the force T or tension T. Calculate the tension T. All right. Now, what does the fact that it's moving with the uniform speed tells us? It's moving in a straight line, we can see, and it's with uniform speed. That means in equilibrium. Okay. Moving in a straight line with a constant speed is also equilibrium. So the sum of all the forces acting on this object should be 0. So where are the forces acting? Why is this object not accelerating? It's not accelerating because balanced by another force of friction over here. Okay, so we have the sum of these two forces, tension plus friction, equals 0. Okay, so we have the tension is the negative of the force of friction. Now, these forces do not have vertical components. Okay, we have only x components. So if you use the component form, we have Tx equals negative Fx. Okay, so what do you know about tension? Well, we don't know its magnitude, but we know its direction. Its direction is 0, it's going east. How about the friction? We don't know its magnitude so far. Well, let's just say F, but its direction is 180 degrees. Okay, so this is saying the tension times cosine of 0 equals negative friction times cosine of 180. Okay, so cosine of 0 is 1, so you get T equals, this is positive right now, but cosine of 100 is negative 1, so you get negative F. Alright, so tension is the negative of the force of friction, but we also know force of friction is mu times the normal force. Okay, now we have other forces over here. You got the surface pushing up, the normal force. We got the weight pulling down, which is the weight. Okay, these two forces are also balancing each other because the object is not moving in that direction. Okay, so well, first we'll write this one. Tension equals negative mu times normal force. Okay, so this is from the x equation. From the y equation, now we have this vertical forces. So this does not contribute to the vertical equation over here. So we have, well, the equation is n plus the weight equals 0. Okay, but if you use the component form, this becomes ny plus wy equals 0. Okay, these two forces are balancing each other. So what do you know the normal force? The normal force, okay, we don't know right now, but its direction, you see, is north, it's 90 degree. How about the weight? Well, its magnitude is mass times gravity, and its direction, theta w, is negative 90 or 270 degrees. So this gives you the magnitude of the normal force times the sine of 90, and then plus the weight, which is mg, times the sine of negative 90 equals 0. Okay, so this is sine of 90 is 1, so you get n. This is negative 1, we get minus mg equals 0. So the normal force equals mass times gravity. All we're saying is, we don't have to go through this, all we're saying is this force is balancing this force. Okay, I'm just trying to be technical about it, but you don't have to go through this to figure this out. Okay, so this would be 10 times 9.8, that is 98 newtons. And see over here, we have the friction is mu times n. So all right, let me read this equation. Okay, let me start from t equals negative f. Do I have fx? Okay, fx is over here, negative f. So we have, let's go to this equation. This would be, well, there's a negative over here, with this negative, it will be positive. Okay, that's what I'll say. You get tx equals negative fx, but this is negative. Well, this was negative over here, but then this becomes positive because we have two negatives, negative, negative. We get T equals the force of friction, and that is mu times n. So the tension equals mu times n, that is 0.2 times 98, which is, I guess, 19.6 newtons. Okay, so that is the tension in the stream. But, you know, all we're saying is this force is balancing the force of friction, okay? And this normal force is balancing the weight, that's it. So you've got the tension is Tx equals negative Fx, but this one is negative, so that makes this one positive. Okay, so you've got the tension equals force of friction, and the force of friction is mu times N, and using the Y equation, we just calculated the normal force. All right, another example. Suppose we have, let's say, this object, let's say once again is a 10 kilogram object. Okay, it's hanging from these two objects. Let's say 37 degrees. Let's say this is 53 degrees. Okay, and obviously it's in equilibrium, right? So what are the forces acting on this object? We got this tension pulling this way, let's call it T1. We got this tension pulling this way, that's T2, and then we got the weight pulling down. Okay, since we know it's at rest, then we can add up the forces and equate them to 0. So you've got T1 plus T2 plus the weight equals 0. Okay, so this is the equation we have to apply. And if you want to use the component form, then that will be T1x plus T2x plus Wx equals 0, and then T1y plus T2y plus Wy equals 0. Okay, so we need the components. Alright, let's start with T1. With T1. What we know? We don't know the magnitude of T1. Well, that's actually the question. The question is calculate T1 and T2. That's the magnitude of the tensions, T1 and T2. We know the directions. We want to find the magnitudes. Okay, so we don't know T1, but we know its direction. Let's call theta 1. So we're going to use default angles. See, 37. These two angles are alternate interior angles, so this one is also 37. Okay, so this is the default angle for this force, because default angles are measured with respect to the positive x-axis. This counterclockwise will be positive, so this is 7 degrees. Okay, so that's what I know. So let's find out T1x and T1y. So T1x is the magnitude T1 times cosine of 37 degrees. Cosine of 37 is 0.8, so this becomes 0.8 times the unknown force T1. And then T1y is the magnitude T1 times the sine of 37 degrees. Okay, that is 0.6 T1. Okay, so we have expressed the components in terms of the magnitude. So that's what we have. T1x equals 0.8 T1 and T1y equals 0.6 T1. Okay, so we're going to need this expressions when we apply these equations over here. And then let's go to T2. Okay, T2 is inclined like this. Okay, and look, these two angles are equal. These are alternate interior angles, if you remember geometry. But the angle we need is this one. This is the default angle measured from here. So the default angle is 180 minus 53. This is 53. So this angle is 180 minus 53. So we have this angle over here. Let's call it theta 2 is 180 minus 53, which is 127. Okay, because this angle over here is 53 degrees. All right, so what do we know about this force? This is unknown. We don't know its magnitude, but its direction is 127 degrees. All right, so we have T2x equals the unknown force T2 times cosine of 127 degrees over here. Okay, so we have the unknown force. Now, if you use your calculator, obviously this is going to be negative because it's going this way. Okay, and it's going to be negative T2 times 0.6. Okay, it's going to be negative 0.6 T2. Okay, how about T2y? T2y is going to be T2 times the sine of 127 degrees, which is going to be 0.8 T2. Okay, so we have the following. T2x equals negative 0.6 T2 and T2y equals 0.8 T2. Okay, so we have this for the tensions. We know their directions, but their magnitudes are unknown. Okay, next let's do the weight. Okay, the weight is pulling down over here. Its magnitude is mg. Okay, you know that the magnitude is mass times gravity, and the direction is also negative 90 degree or 270 degree if you come this way, or if you 90 degree if you come clockwise. So the direction for this one is negative 90 degree. Okay, so we've got Wx equals the weight times cosine of negative 90, it doesn't have x component, and Wy equals mass times gravity times sine of negative 90. Sine of negative 90 is negative 1, so you get negative mg. Okay, and we know the mass is 10 kilograms, so it's negative 10 kilograms, and it's approximately 10, so you got negative 100 newtons. Okay, so what do you have? Wx is 0, Wy is negative 100. Okay, all right, then now we're going to go back to the component equations. Let's start with the equation for x components. T1x plus T2x plus Wx equals 0. So we have T1x plus T2x plus Wx equals 0. All right. Now we have expressed T1x in terms of the magnitude T1, and this will be over here. T1x equals 0.8 T1. So this one is 0.8 T1. And T2x is over here. T2x negative 0.6 T2. So you've got minus 0.6 T2. The x component of the weight is 0. It doesn't have a horizontal component. So you've got plus 0 equals 0. Alright? So we have the following equation. 0.8 T1 equals 0.6 T2. If you want, you can multiply the equation by 10. So you got 6 T2. Or we can solve for T1. So you've got T1 equals 6 over 8 or 3 over 4 of T2. So the tension T1 is 3/4 of the tension T2. But we have two unknowns. We cannot solve the problem just from this equation. We'll get another equation. And the other equation is a y equation. That is T1y plus T2y plus Wy equals 0. Okay? So what is T1y? T1y is here, 0.6 T1, right? So that is 0.6 T1. How about T2y? T2y is right over here, 0.8 T2. So you've got plus 0.8 T2. How about Wy? Wy is negative 100. Negative 100 equals 0. Okay? So we have this equation, 0.6 T1 plus 0.8 T2 equals 100. If you multiply the whole equation by 10, we have 6 T1 plus 8 T2 equals 1000. Okay? So we have two equations. We have this equation and this equation. So there are two ways of solving these problems, either method of elimination or method of substitution, but in this case it looks like substitution is easier. So you can just replace T1 by 3/4 T2 over here, and that'll give us an equation in one variable. Okay? So instead of T1, I'm going to put 3/4 T2 over here. Okay, I'm going to take this one, I'm going to put over here. Okay, so that gives me 6, 3 over 4 T2 plus 8 T2 equals 1000. Okay, so we multiply the whole equation by 4, so this gives me 18 T2, and then times 4, this is 32 T2, and that's 4000. Okay, 4000, and this is 50 T2, so we've got 50 T2 equals 4000. So T2 equals 4000 divided by 50, which is 80 newtons. Okay, so T2 is 80 newtons, and T1 is 3/4 of that. And T1 is 3/4 of T2, or 3/4 of 80, which is 60. Okay, and the solution. So we've got T1 equals 60 newtons, and T2 equals 80 newtons. Okay, that's the solution. Alright, so the main thing is, if you know an object is at rest, you can add up all the forces and equate them to 0. Okay, which is this equation over here. Now you can use this equation with the IJ notation, but also you can decompose this equation into algebraic equations. As you add all the x's, equate them to 0, all the y's equate them to 0. And then the next step is to find the components in terms of the unknowns. Okay, once you do that, it's just plugging it into the x and y equations. Let's look at another example. Suppose, let's say we have the following situation. We have a string over here, and then let's say we have another string over here, and then we have weight hanging over here. Okay, let's say this is 37 degrees, this is horizontal. Once again, let's say it's 10 kilograms. Okay, so in this case also we have two tensions. We have tension T1 going this way, we have tension T2 going this way, and you get the weight pulling down. Okay, so this object at rest, you get these three forces, the same thing. So we do T1 plus T2 plus the weight equals 0. But if we rather use the components, then we'll say T1x plus T2x plus Wx equals 0. T1y plus T2y plus Wy equals 0. Okay, so let's look at the tensions. So tension, the direction is 37. Okay, so you've got this tension T1 over here is the unknown tension T1 times cosine of 37 in the I direction plus T1 sine of 37 in the j direction. Okay, so that is 0.8 T1 in the I direction plus 0.6 T1 in the j direction. So from this we see that this is the x component, the y component. So you've got T1x equals 0.8 T1, and then T1y equals 0.6 T1. Okay, and then we can do the same thing to the tension. Now, for T2, of course, we don't know the magnitude, that's what we're looking for. How about the direction? The direction is west. This tension is pulling this way, so it is 180 degrees. Okay, 180 degrees. So we can say this tension over here is the unknown T2 cosine of 180 degrees in the I direction plus T2 sine of 180 degrees in the j direction. Okay, so this one is 0 because it's 0, and this one is negative, so you've got negative T2. Okay, so that is in the I, and this is 0. Okay, so that tells you the x component is negative T2 and the y component is 0. Okay, alright, so these are the components for this one. About the weight, the weight is mass times gravity, and its direction is negative 90 So the weight is mg cosine of negative 90 in the I direction plus mg sine of negative 90 in the j direction. Okay, so cosine of negative 90 is 0 and this is negative 1. So the weight is simply negative mg in the j direction. Okay, mass is 10, this approximate 10 is going to be negative 100 in the j direction. So does that mean wx is 0, no I component, and wy is negative 100. Okay, so now we go to our equations. The first equation is t1x plus t2x plus wx equals 0. Okay, so t1x is 0.81, 0.81. t2x is minus t2, and wx is 0, we get 0. Okay, so we have from this equation we get t2 equals 0.81. Okay, now let's look at the y equation. t1y plus t2y plus wy equals 0. t1y is 0.61, 0.61, and t2y is 0. Okay, how about wy is minus 100. Okay, minus 100 equals 0. So we've got 0.61 equals 100. So you can solve for t1 from this equation. So t1 is 100 divided by 0.6, or 1000 divided by 6, 1000 divided by 6, and then that's 500 over 3. That's 500 over 3 Newton. Okay, and then we have this equation over here, t2 equals 0.81. So t2 equals 0.81, and that is 0.8 500 over 3. So this is 8 times 50, maybe 400 over 3. 400 over 3 newtons. Okay, so we have the solution. T1 is 500 over 3 newtons, and T2 is 400 over 3 newtons.